plastics are pretty amazing. Everything from building and construction to fabrics and fibers, consumer products, transportation, packaging, of course, you know, they've transformed our daily lives like no other material in the last 100 years. They're so useful, they're so economically viable, they're so strong and lightweight and versatile that they've become integral to our existence. And they provide a lot of benefits. And that's why it's a $650 billion market. It's absolutely huge and growing year over year. But plastics, as you know, have a problem. They don't go away. In fact, it's estimated that around 80% of all the plastics that have ever been produced are still here somewhere. Only around 11% has been incinerated, and only around 9% historically has been recycled. And we've designed all of these materials to be super durable. But that, as you know, has caused a huge environmental problem. We make over 760 billion pounds. Some even estimate higher than that, around 900 billion pounds of plastic every year. And around 30 to 36% of that is packaging or short-term use applications. And currently only around 4.5% of plastics are being recycled. Back in 2018, China instituted their National Sword program, which essentially shut its doors to incoming recycling from the US. And it's really wreaked havoc on the recycling world. And it's really reduced the amount of plastics that are actually being recycled. Basically, if it's not a milk bottle or a PET container, there's very little that's actually being recycled. People call it wish cycling, putting everything in the recycling bin, when the truth is that not a lot of that is going to be recycled if it's not a milk bottle or a PET container. And unfortunately, you know, as much as we try to do the right thing, all of our collection systems are leaky. And over 18 billion pounds of plastic ends up in our oceans every single year. And to give you an idea of what 18 billion pounds of plastic looks like, that is 5 grocery bags full of plastic trash for every foot of coastline around the globe. If you can imagine every foot of coastline you've ever seen, 5 grocery bags full of plastic trash every single year go into the ocean. It's a huge problem. So where are these plastics coming from? Well, if we look at where plastic resins lie in terms of their manufacture, the bulk of plastics go into the packaging and short-term use market. Around 36%, the blue line you see here, is packaging and short-term use. So if you picture a third, over a third of all the resins that are made go into these packaging and short-term use applications, you can see where the problem lies. And although it's around 36% of the resins that are made go into packaging, the truth is that around half of the plastic waste that's out there comes from packaging. So if we want to make an impact, if we really want to make a dent in this problem, that's really where we need to look. If you look at the manufacture of resins, the top 5 resins are listed here. Polypropylene, low density and linear low density polyethylene, high density polyethylene, PVC or vinyl, and PET. And polyolefins are a family of polymers that include both polyethylene and polypropylene. And that's really where we're focused, because that is really the root of the problem. So we all grew up with this mantra of reduce, reuse, and recycle. And Radical Plastics wants to put a 4th R onto that list, and that's redesign. Let's start redesigning these materials so that they can function, do their job, be economical, provide the barrier and the great properties that we expect of plastics. But if they leak into the environment, let's design them with a fail-safe built in so they don't live in the environment for decades, if not centuries. So with that intent in mind, Yelena really set out to find a unique chemical solution. How can we make something that's both economical, that's recyclable, but if it ends up in the environment, won't last forever? And that's where we developed the Radical Plastic solution. It starts with this fine mineral powder called fine mineral matter. And it's basically a very fine gray powder made up of transition metals, alkaline earth metals. It comes from the ground. And we use that to make a catalyst system that we add only 0.5 to 1% into regular plastics. We melt blend this with regular plastics to develop this fully formulated pellet. And by controlling all of the ingredients in that pellet, including the catalyst, we can control the rate of degradation and also the onset of degradation. So we can control essentially the service life of that material through this patented technology. This material is really a drop-in replacement for what plastics producers are using now. They would buy this pellet and then just drop it in the hopper of the extruder, just like they would regular plastic. The difference is significant though. If this material ended up in the environment, it would undergo a traditional two-stage degradation process. Our catalyst really acts in the chemical phase. If this material were littered into the environment, leaked into the environment, the catalyst would kick in and start this regenerative free radical reaction. And what we're doing is we're taking these long polymer chains that microbes cannot digest, and we're cutting them down into smaller and smaller and smaller pieces called oligomers. And we're also changing the chemistry of the material. We're adding oxygen groups onto the backbone of that polymer so that it is wettable, essentially. As you know, most plastics are hydrophobic. If you put water on them, they bead right up. This allows oxygen onto the backbone of the polymer, making it more wettable, so microbes in the environment can adhere to it and consume it. And this stage, the material is essentially a biodegradable wax. It's very low molecular weight biodegradable wax that microbes in the environment see as a food source. They can metabolize this material, turning it back into biomass, CO2, and water. And this catalyst, unlike some of the pro-degradant technologies that have been tried in the past, this is a regenerative catalyst that isn't used up, but it keeps working until the material is completely transformed into that biodegradable waxy form. So we've been talking a lot about packaging and about the plastic pollution problem, which in large part is caused by packaging. But having been in the industry for many, many years, I know that packaging is hard. It's really complex. It has a lot of requirements, including food contact notification, barrier, printability, clarity. So when we thought about a target market as our beachhead market, we decided to go with agriculture because this is a very urgent problem for farmers and growers right now. The fact that they have plastic on their farms that they don't know what to do with. And it's actually a $6 billion global market. Agriculture buys $6 billion of plastic a year. The bulk of that actually is sold into plastic mulch films. It's around a $4 billion a year market. And this is a 1 mil black polyethylene. It can be anywhere from 0.8, 0.6, 0.8 to 1 mil or 25 micron black polyethylene film that farmers lay down in their fields to reduce weeds, to reduce their water usage by as much as 10 times, and also to increase their crop yield and quality. It's a really important tool for modern farming. But it is polyethylene. So at the end of the season, the growers have to pay to have all of this film, miles of film, collected and disposed of. It's really hard to recycle because it's covered in dirt and fertilizers. So it's either usually incinerated or landfilled, and that's expensive. In addition, by removing these films, you're removing the topsoil of, on the farm. And that's also a concern because that topsoil is very, very valuable. So the difference is if they just replace that polyethylene film with a radical plastics film, they can till it into the soil where it will biodegrade before the next growing season. It leaves no microplastics and has no ecotoxicity effects on the soil. And in fact, our mineral catalyst is actually being sold into agriculture now to be used as a soil amendment or a soil conditioner. It makes the soil healthier. So for this application, again, we're providing a product that looks and acts and feels just like regular plastic, but it doesn't need to be collected and disposed of at the end of the season. So it saves the farmer time and money. And because a lot of this film is actually incinerated either at an incineration site or even just on the farm, by eliminating that incineration step, we can reduce the greenhouse gas impact of this product through its life cycle by around half. Now, where we are in this process, in this commercialization process, is we're in a technology validation stage. Last year, we made a few dozen rolls of this mulch film, and we tested it in 7 different locations around the US, different crops, different climates, including the Wegmans Test Farm in upstate New York, which is relatively cold, and the University of Florida, where we made over 2,400 watermelons on our film. And the feedback we got was incredible. They said, my gosh, you know, unlike some of the starch-based and other biodegradable products that are out there, this looks and feels and acts like regular plastic. And yet I was able to till it into the soil. So we got very, very good feedback kind of across the country on this film. We also got samples back, and we looked at the polyethylene film after it had been in the field versus the radical plastics film. And after only 2 months of exposure, we saw exactly what we were hoping to see. This is an FTIR scan, which shows you essentially the chemical composition of the film. We saw no change really in the polyethylene film, which is what we would expect, but the radical plastics film already had those really key chemical groups, those oxygen groups we're seeing on the chain. We're showing that we are in fact changing the material chemically on both sides of the film, not just on the top surface, on both sides of the film, and even the film that's buried into the soil. We're seeing this significant chemical change that is caused by the catalyst. As soon as the catalyst is exposed to those outdoor conditions of oxygen, UV, heat, that's what kicks off the catalyst. And we're already seeing that change after only 2 months of exposure, which is really exciting for us to see. So in addition to the field work, we're also doing lab work. One of the reasons also that we chose agriculture actually is because there's a well agreed upon standard that says if you pass this test, you are confirmed to be biodegradable and safe for the environment. That test doesn't really exist in packaging. There's no mutually agreed upon test that says this is the gold standard that you can pass in packaging that shows everybody that you're biodegradable in the environment, not in industrial composting, but in the environment, and that you're safe. So that standard is a relatively new standard out of Europe called EN 17033. And we're currently testing to that standard at 2 different labs in Europe. We expect some initial results in April, and then our final results probably around October of this year. So we're really eagerly awaiting those results because, as I said, we're starting out in agriculture, but the bigger problem really is in packaging and in other thin film applications. That's really causing the plastic pollution problem. So that's where we need to be if we really want to make a dent in the problem. And that is definitely our intent. And as we discussed, a lot of the packaging that is out there, actually around 57% of the packaging that is collected is either polypropylene or polyethylene. It's these polyolefin films that we already know how to design this catalyst for. That said, this technology could also be expanded to other polymers like vinyl, like styrene, like acrylics, other polymers that might leak into the environment. But we're starting with the low-hanging fruit, quite literally. And once we prove this technology in agriculture in 2021, we'll be ready starting in the 4th quarter to expand into other more impactful applications such as packaging. Because as you can see, it's a very urgent and a very visible problem, and brand owners are feeling it. And they want to find a solution, but they don't want to give up the great properties and economics of conventional plastics. So we've only been at this full time around 18 months, and we've already received a lot of different accolades, including a USDA grant, and we're applying for our next phase 2 USDA grant in May. And things have been going very, very well, including another grant from the Mass Clean Energy Center, which is very exciting. Because our solution, we really see this as a game changer. We see it as a drop-in replacement for what people are using now. It's still economical. It still processes on standard equipment. It still has the same performance as conventional plastics because we're only using 0.5 to 1% of this mineral catalyst. Really importantly, it's still recyclable along with conventional plastics. So if you have a plastic bag and a radical plastic bag, they can be recycled in the same system. However, if these materials leak into the environment, they have that built-in fail-safe so that they won't exist forever. They'll degrade in a matter of months. So we hope you'll join us in reducing, reusing, and recycling, but also in supporting redesign of plastics to make more sense. And that's all I had for now. So I'm going to stop share, and I would love to take any questions you guys might have.
Great. I think Brittany and I are going to tag team on asking the questions right now. James, do you want to turn on your microphone? You can ask directly. No? Okay, I can ask as well. So James asks, what is the impact on performance and how does the formation change WRT petroleum?
With respect to petroleum, okay. Great. So the impact on performance of the material, thus far, the physical property testing that we've done, some of which we've done at Endicott College, by the way, has shown really we're not affecting the physical properties of the film. The only thing that is slightly affected is the color, because this is a mineral filler, it's a dark gray material. So we do see a slight mineral tint to the film, even though it's very, very clear. But we haven't seen any changes in tensile elongation, dart impact, barrier, COF or coefficient of friction, printability. We haven't seen any changes with respect to the physical properties of the film. And then in regards to petroleum, how does the formation change with regard to petroleum? We've made both bio-based polyethylene versions and petroleum-based polyethylene versions. The only difference is essentially where where the ethylene comes from. Does it come from corn or does it come from petroleum? Our catalyst works the same with both bio-based polyolefins and petroleum-based polyolefins. But what we're buying, quite frankly, is we're not buying an off-the-shelf resin. We're buying the resin one step back in the process. We're buying a barefoot resin with no additives in it whatsoever, a food-grade barefoot resin. And we're selecting very carefully all of the additives, antioxidants, stabilizers that we put into that pellet to make sure that when it degrades, it's fully safe. I hope that answers the question.
I think it does. And his follow-up question was, can it be used on certified organic farms? Have you determined that?
Great question. Great question. If we use bio-based resins, it can be used on an organic farm. We would have to be certified, but we would have to make a fully bio-based resin version of this. Our first product out of the gate will be a petroleum-based, because we want to take advantage of the economics, and the bio-based plastics are more expensive. And the bulk of the market is conventional farming. So that's really our first target, using petroleum-based polyethylenes, but we could create a bio-based version for organic farming.
I'm back, by the way. I was doing my lunch dishes, so I couldn't get to yeah. So I've got several friends who are in the organic farming community who have, for example, Green Meadows Farm in Hamilton. They went from organic to non-organic, and they just tilled the plastic back into the soil. It was just an awful development. So yeah, it was really, it's just bad. But I've got a lot of friends who are interested in this type of thing. So I'd like to reach out to you, Chris, and talk a little bit more about it at some point. So I'll get in touch. And I'm a member of the NSTC. I know Tom and everybody over at NSIV very well. So I'll reach out and you'll hear from me sometime soon.
Excellent, excellent. Yeah, that would be great. And again, our first target is conventional farming. And then, kind of our next generation would be an organic version. It would have to be OMRI certified. But it would have to be based on bio-based resins. I hope that answers your question. We're already working with the Braschems and the bio-based polyethylene guys anyway. We already know which grades to use. It's just that we chose to go out first with a more conventional product.
That's great. Thank you. Yeah, that answers my question. Appreciate it.
Great. So I'm actually going to ask Bonnie to unmute and ask her next question out loud. Bonnie, are you there?
Yes, found the unmute
Awesome.
button. This is kind of on the same subject, but when people were introducing themselves, there was somebody who talked about the earth-friendly food production. And I was just wondering if there's anywhere locally where you can buy food that has been grown in that earth-friendly way. I didn't get the name down of who it was.
Maybe somebody could put that into the chat and we can move on.
Okay, it's in the chat.
Great.
Yeah, okay. Sorry about that.
No, I think probably there's some people who have some good ideas here. So let's put that in the chat.
Yep.
Brittany, you want to do the next one?
Yeah, would encourage people to answer that, because I'm also curious, and let's network with each other. Let's see, Dan, that's not really a question. Okay, Colin has a question. When you recycle products made with modified resin, how do you prevent the decomposition cycle from kicking in too early in the new product?
Yep. Okay, for example, he says if the material is reused in something like a milk bottle, how do you prevent the milk bottle from degrading on the shelf? Great question.
Exactly.
So when you recycle materials, as you might know, you generally add a lot of antioxidants and stabilizers to stabilize that, that PCR material, the post-consumer resin material. Any kind of standard antioxidants and stabilizers that they would use in the recycling process, in the melt recycling process, would counteract our catalyst. So it wouldn't have the ability to kick in the recycled resin, if that answers your question. And that's pretty typical practice is to add, stabilizers in while recycling.
Oh, that's really cool. Thank you.
Sure.
Timothy has an interesting one here. I would like to think a plastic sheet laid out on the ground would get plenty of UV light and O2 more than after it was tilled into the ground. So wouldn't it tend to degrade before the farmer was ready to harvest?
That's a super question. That's a great question. The way that we are designing these materials, the catalyst is there from the beginning. And what we do to stave off that degradation reaction is we add inhibitors. And we can change the type and amount of inhibitor that we add. The films that we're providing now to agriculture are designed to last around 4 months before they start to degrade. Once that inhibitor is gone, then the catalyst can kick in and start to degrade the material. For something like packaging or bags, we would likely extend that service life to maybe a year or even 2 years. We would want that to be super stable for a year or 2 years. That said, if a product is sitting on a shelf, interior light isn't enough energy to start activating that catalyst. It would have to be outside in the UV. But that's the way we do it, is by incorporating certain inhibitors and dialing in that time frame.
Interesting. So I think our next question from Joel really gets to some of the costs issues that you brought up and the comparability. So how does it compare in terms of standard plastics now and under some projected economics in the future?
That's a great question, Joel. Excellent. And our issue with bioplastics, again, when we were trying to bring them into the market, is they were anywhere from 2 to 10 times anything we were trying to replace. And it really had to make a lot of sense. It really had to have a compelling value proposition to get someone to buy something that was 5 times more expensive. So I know a lot of the bioplastics are a lot more expensive, and that has been a real challenge. In addition to the fact that they can't go in the regular recycling stream. Those are 2 really big challenges for bioplastics, but cost is the big one. And what we learned is that anything that's really going to replace conventional plastics has to be almost price parity. People aren't going to pay double for something just because it's green, for example, the mulch film applications, this is just round numbers. Say the regular polyethylene is $1. The biodegradable versions that are out there right now are anywhere from $2 to $3 a pound. So they're double or triple. Whereas our product, again, we're just using around 1% of this fine mineral catalyst in regular plastics. Now, it is more expensive right now because we're using a toll compounder. We're not going to build a plant. We're using a toll compounder and paying them by the pound to melt blend all of these materials together for us. So right now, going into the market will likely be 1.5 to 2x. But long term, we can take this technology and back it up in the supply chain. So an ExxonMobil or a Dow can be producing durable polyethylene on one line and radical polyethylene for short-term use applications on the next line. And theoretically, that can be done at price parity. The catalyst itself is not that expensive. It's just that additional step that we're introducing right now as we're coming into the market that adds additional cost. So that was really our goal, is to bring out something that we could do at price parity.
That's awesome. Really interesting. So then our next question kind of lends nicely into the end of that one from Tom, asking, what's your next steps? How do you plan to go to market? Do you need a license for the technology,
Right.
or is making a physical product?
Right. Great question. We're going to be selling the physical pellets to people who are already producing plastic film. So we're using a local toll compounder here in Massachusetts. We are shipping in all of the ingredients, and they are charging us by the pound to make our secret recipe. And at the end of the day, we have gaylords full of plastic resin that we're selling to people who are already making film. And that's how we're going into the market. That will likely be the same with packaging suppliers or bag suppliers. That said, the plastics market is so fragmented. There's just so many applications out there that there's definitely a possibility to license in kind of parallel technologies. We had a call just yesterday with someone who's doing nonwovens for medical applications like wipes and drapes and masks. And they're getting a lot of flack these days because polypropylene, if it ends up in the environment, doesn't go anywhere. So that might be a case where, you know, we don't have the manpower to develop a non-woven grade right now and to develop that product for you, but we will license the technology, you know, to you for that application specifically. So there's a lot of potential to license, whether it's technology based or geography based, because we do want to proliferate this technology and make sure that the products that don't need to last forever, you know, we can design them so that they don't last forever, and just we don't have the manpower to do it all ourselves.
Wow. So that would really multiply your applications.
It would, but some of these are, you know, the most impactful ones are really, they're relatively easy. Something might, the advantage, example I always give is bread. If you've ever gone to the grocery store to buy a loaf of bread, what do you do first? You look at the expiration date, right? And it's around a week or 2 weeks maybe. But, you know, we're packaging that bread in something that if it leaked into the environment would last for decades. You know, it doesn't make any sense. So we need to have something that's economical, that still has the barrier, that protects the product. But if it leaks into the environment, you know, it'll degrade harmlessly.
Mary Jane has a question, and I'm not sure I understand it completely. So I'm going to let, if she's there, she can jump on. Has to do with interest in working with a thermoformer.
Oh, yeah.
Yes. So this is Mary Jane. I was just, you know, it's very cool that you're starting in the agriculture space. I think that's a wonderful thing. But I was just wondering if you had thought or partnered with anybody yet in the thermoforming space, you know, considering single-use plastic. And of course, that's such a big problem out there, is what do you do with that and how do you replace that?
Right.
And I asked that because, as I said, I used to work for one, so I could definitely make an introduction for you if you were interested.
Well, thank you. I think we would love longer term to work with a thermoformer. We're not quite there yet. We don't have a thermoforming grade, but there's a lot of applications, deli trays, you know, for example, if you've ever walked through a Wegmans and you see these, you know, single use or, you know, berries or something, those are all thermoform containers. And this would work on polypropylene, polystyrene, the materials that are used in thermoforming. So that's definitely a future application for us. But as you know, it requires a lot of melt strength because you're melting it and then you're drawing it down. And we don't have a grade that's specifically designed for thermoforming yet, but longer term, that would definitely be of interest.
Okay, cool, great, thank you.
Mm-hmm.
So it looks like Allison has a question here. Do you think there will be a moral incentive as well as a financial one in the oil and chemical companies such as Dawn and Exxon? Do you have any support in these companies?
Very good question. There's definitely both a moral and a financial incentive for companies like Dow and ExxonMobil who are producing conventional plastics right now to look at this type of technology. In terms of do we have their support, we've talked with all of the major chemical companies and they're all extremely interested in looking at what we're doing. Honestly, because they can continue to make plastic and you know, make something that is better for the environment, offer something better to their customers. We don't have any agreement signed currently with the major with the major chemical companies right now. As I said, we're really focused on getting this proven in agriculture. By the end of this year, we will show that, you know, it is safe, it does biodegrade, it doesn't create microplastics, and we have market traction. And that's, I think, a good opportunity for us to go and, you know, talk to these big guys and say, hey, you know, by backing this up into your process, we could really start to make an immediate difference in this plastic pollution problem.
Yeah, I think that's a really great point. Really cool. Julie, you want to ask one more?
Yeah, and maybe combine one. So we did have a question about the agricultural, whether it can be used equally well in greenhouses. And then just to get another one quickly in, there's a question about what is the impact on CO2 release when these are tilled into the soil?
Good question. I guess I'll go one by one. Greenhouses we haven't investigated if it sees enough UV. I think it would depend on what that greenhouse is made of. Does it filter out the wavelengths that we need in order to start our catalyst working? So it would really depend on the type of greenhouse. We haven't done that work yet, but it could potentially work. We just don't know yet. And in terms of the greenhouse gas releases, when it biodegrades, it does, absolutely. When the microbes, and that's actually how we test it. We take pieces of this plastic and we put it in this glass container with a top on it with microbes in it, and we see the CO2 that comes off, and we're showing that the material is degrading, microbes are eating it and producing, respiring CO2. So we are creating more CO2 because the microbes are eating it and respiring CO2, but it's over a much, much longer period of time. Whereas something like incineration, first of all, it requires a lot of energy to initiate the incineration, and then it's releasing greenhouse gases all at once. So it's a significant difference if you look at from a life cycle assessment standpoint, if you're allowing it to biodegrade.
Great. Brittany, do you think we're done, or do you want to take some time to talk about?
There's so many more questions. Let's see.
Let me see. Oh, there's one about thermoset plastics. They've only recently learned how to make thermoset plastics reusable. Any chance this technology could be extended to those types of plastics? So in terms of thermoset plastics, there's two different general categories of plastics, thermoplastic and thermoset. Thermoplastic can be remelted and reformed. Thermoset, once you cross-link them, they are set and they can't be remelted. So this technology, I don't think would be suitable for thermosets. Those are usually toward really durable applications. If you have an old frying pan, for example, from the, from the 70s, it probably has a thermoset really heavy handle on it. And those were really designed for durable applications. So we're not designing catalysts right now for thermoset. We're really just focused on the thermoplastics. Now within thermoplastics, plastics degrade in two ways, either through oxidation or through hydrolysis. Those are the two ways that plastics degrade. We're focused on the polymers that degrade through oxidation. So those are the polyolefins, polyethylene and polypropylene, but it could be translated to others like vinyl, acrylics, styrenics, styrenes, materials like that. Where it's not suitable is for hydrolyzable polymers. And hydrolyzable polymers include the polyesters, the PET materials. That's why some bioplastics like PLA and PBAT, PBS, the polyester-based bioplastic, they need to go to hot composting in order to biodegrade. They need to go to industrial composters in order to biodegrade because hydrolysis can only happen at those temperatures. You can't catalyze it to happen at ambient conditions. So we're really focused on all the oxidizable polymers, which makes up the bulk of the plastics and certainly the bulk of the plastic pollution problem.
Awesome. And we actually, sorry, just scrolling back up, there's a few more. So Michelle asked, and Michelle, if you want, you can unmute. How is your, sorry.
Sure.
Hi, Michelle.
Can you hear me? Hi,
Yeah.
how are you? So I follow a company called Impact Snacks.
Okay.
And one of their claim to fame is about sustainability in terms of their underlying product and their wrapper.
Mm-hmm.
And the wrapper is supposedly 100% biodegradable because it's using cellulose technology. How is that
Sure.
different from what you're doing?
Right, it's quite different. That's a true bioplastic material based on cellulose. Cellulose in general is a natural material. If you've ever gotten like a envelope with a window in it, those used to be all cellulose. Cellulose is very kind of crinkly and loud. They used to be used to like wrap hard candies because they're very, very wrinkly and loud. But that is a true bioplastic. It's a lot more expensive. It doesn't have the barrier properties of polyethylenes and polypropylenes, and that's why cellulose has been limited in terms of its applications, especially in the snack packaging area, quite frankly, where you need both water vapor transmission and oxygen transmission to be very, very low. But cellulose is a biodegradable polymer. It's just a lot more expensive. It's a lot harder to work with, and it doesn't have really the physical properties of most of the plastics that are used in packaging.
Great, so I think we're gonna have to call it here. So Kristen, thank you so much. This is fascinating. And I feel like I could listen to the presentation 2 and 3 more times and learn something new. And but good luck with everything. We hope to see your product out there commercially very quickly. Brittany, you want to talk about the April event?
Yeah, Kristen, I actually want to ask if you're comfortable with giving out your contact information.
Okay.
Quite a bit of people are asking for it, so
I will put it in the chat, and I just want to thank everyone for your great questions and for your attention. And if you have any follow-up questions, feel free to drop me an email anytime.
awesome. Thank you. I appreciate that. And we will follow up with all the attendees with also Kristen's contact information in that email. So thank you, everybody. So just quickly as a reminder, next month is Earth Month. I don't know if technically it's Earth Day, but at my company, Revision, we celebrate Earth Day all month long. So next month, April 14th at noon, like Tom mentioned, this is a monthly presentation, and we will always take suggestions if you have topics and speakers that you want to present. But Endicott College will be joining us next month to talk about everything going on the campus there that is sustainability focused, and they'll be talking to us about how to celebrate the planet during the month. And normally they do an Earth Day event. I know it got canceled last year, so we look forward to hearing from them on ways to celebrate without the Earth Day event. So please sign up for that event. You will see an email coming out soon if you're on our email blast. And yeah, you can sign up on the website as well. So thank you everybody so much for coming. It means a lot to us. We are a volunteer board, so having you show up day of means a lot. So thank you, Kristen, for joining today. Thank you everybody for attending. Hope you enjoyed it, and we'll see you next month. Bye, everybody. Thank you.